Algorithms, session A5 of the FSTTCS 2021. So the first talk is going to be given by Eklavya Sharma, and it's going to be on harmonic algorithms for packing d-dimensional cuboids into bins. So over to you, Eklavya.
Thanks. Hello, everyone. I'm Eklavya. I'm currently a PhD student at the University of Illinois at Urbana-Champaign. And today I'm going to talk about my work on harmonic algorithms for packing d-dimensional cuboids into bins. And this work was done when I was a master's student at the Indian Institute of Science, Bangalore, and there I was advised by Professor Arindam Khan. This work is about the geometric bin packing problem. So let me start by defining what this problem is. So in the two-dimensional geometric bin packing problem, which I'll abbreviate as 2BP, we are given a set of n rectangular items, and we're given an infinite supply of identical rectangular bins, and our task is to pack these items into the minimum number of bins. So in our work, we only focus on axis-aligned packing, which means that the edges of the items should be parallel to the edges of the bins. There are actually two versions of this problem. There's a version where we need to pack the items as is without rotating them, and there's a version where we can rotate some of the items by 90 degrees. Similarly, there's a three-dimensional version of this problem where the items and the bins are cuboids. And rotations are slightly more complicated in 3 dimensions because each item can have 6 possible orientations depending on which axis we rotate it about. And in fact, we can extend this problem to d dimensions for any constant d greater than or equal to 1. When d is equal to 1, then we get the classical bin packing problem. And when d is strictly greater than 3, then this problem gets hard to visualize. So in this talk, I'll only focus on the case where d is at most 3. So let's now look at some applications of this problem. So two-dimensional bin packing is used a lot in the metal and wood cutting industry. Here we're given a lot of standard sheets of a standard size, and from that we want to cut out smaller rectangular pieces of different sizes. And so this is exactly the two-dimensional geometric bin packing problem, and here rotations are generally allowed. Another applications is when we want to place advertisements in a newspaper or on a website, and here rotations are forbidden. And three-dimensional bin packing finds applications when we want to pack a lot of boxes into shipping containers for transporting them. Here rotations are allowed, but sometimes there are orientation constraints. For example, some items are fragile, and so they'll need to have a certain face on top. So we can only rotate it about the vertical axis, so there will be only 2 possible orientations. And let's say there's a very long item, and we don't want to keep the item on its smallest face because then the pressure on this face will be large and the object can get damaged. So of the 6 possible orientations, 2 are forbidden and 4 are allowed. D-dimensional bin packing is NP hard, so we turn to approximation algorithms. For an algorithm A, the asymptotic approximation ratio, which I'll abbreviate as AAR, is defined as the smallest constant alpha such that AI, which is the number of bins used by algorithm A to pack the items I, is at most alpha times opt I plus little o of opt I, where opt I is the minimum number of bins needed to pack I. For example, the number of bins used by the next fit decreasing height algorithm to pack the set I of items is at most 4 times the minimum plus 1. So for this algorithm, the asymptotic approximation ratio is at most 4. The asymptotic approximation ratio is a standard benchmark for bin packing algorithms, and a smaller AAR means a better algorithm. So let's now look at some of the best known algorithms for this problem. For two-dimensional bin packing, Steinberg's algorithm has an asymptotic approximation ratio of 3, and it works for both the non-rotational and the rotational version. And in 2014, this was improved to around 1.405. And this works for the non-rotational version and also for the rotational version. But in the rotational version, it's required that the bins should be square. Only then will we get this asymptotic approximation ratio. Okay. In 3 dimensions, Miyazawa and Wakabayashi gave a 4.89 approximation algorithms that works for both the non-rotational and rotational version. Epstein and Vansky then improved the AAR to around 4.5, but their algorithm only works for the rotational version, and that too for the special case where the bin has a square base. And then Caprara significantly improved the asymptotic approximation ratio to around 2.86, but their algorithm only works for the non-rotational version. So we can see here that there's now a large gap between the rotational and the non-rotational version. Okay. In fact, Caprara's HDH algorithm can be extended to D dimensions. And in D dimensions, they get an asymptotic approximation ratio of T infinity to the power D minus 1, where T infinity is called the harmonic constant and its value is approximately 1.69. So these algorithms, some of the algorithms that we saw have shortcomings. Some of them don't allow rotations, and some of them assume that the bin is a square. And all of these algorithms are inflexible with respect to orientation constraints, which means that most of them don't allow orientation constraints at all. And the ones that do allow them only allow certain specific kinds of orientation constraints. So our work not only addresses all of these shortcomings, but it also improves the asymptotic approximation ratio for the rotational 3-dimensional bin packing problem. So we give two algorithms for rotational d-dimensional bin packing. We give the full H algorithm, which is a simple algorithm, and it has an asymptotic approximation ratio of T infinity to the power D, and it runs in n log n time. And we give another algorithm called the H gap algorithm that has an AAR of T infinity to the power D minus 1 times 1 plus epsilon, where epsilon is a parameter to the algorithm and its running time is a large polynomial. So the H-gaps algorithm's asymptotic approximation ratio matches that of Caprara's HDH algorithm. And this now closes the gap between the rotational and non-rotational versions of D-dimensional bin packing when D is greater than or equal to 3. Okay. So let's now do a head-to-head comparison of our work with prior work for 3-dimensional bin packing. The full H algorithm gives us an asymptotic approximation ratio of 4.836, which already does better than the algorithm of Miyazawa and Wakabayashi. And the H-gap algorithm gives us an AAR of around 2.86, which matches that of HDH. So to conclude, we gave better algorithms for the rotational versions of D-dimensional bin packing, which not only improves the asymptotic approximation ratio, but also fixes some of the shortcomings of previous algorithms. Now, there are a few nice important open problems there. The first is that can we do better than the harmonic decreasing height algorithm for 3-dimensional bin packing? And this has been an important open problem since 2008. And another good question is that can we get more practical algorithms? Because HDH and HGAP are very slow algorithms. So Caprara gave an algorithm which is like a mixture of HDH and the first fit decreasing algorithm that has a slightly worse asymptotic approximation ratio, but it runs in n log n time. But this only works for non-rotational versions. So can we extend this to the rotational version? This is another good question. Yeah, that's it. That's all for my presentation. Thanks.
Thanks a lot, Eklavya. Any questions?
Does your work address the concern that can you handle 4 of the 6 orientations for the 3-dimensional case?
Yeah.
Okay.
Yeah, we can handle all kinds of orientation constraints.
What do you do? How do you encode that? Only these.
So we encode this as a multiple choice bin packing problem. So we express the problem instance as a set of items, and each set contains is like an enumeration of all possible orientations that we allow. So this actually extends to more than just orientation constraints for each. So think of it like for each item we have multiple choices available. That let's say you're packing your luggage and there are multiple of different kinds of shampoos and you need to pick one. There are multiple soaps that you have and you need to pick one. So even these kinds of problems can be solved by our algorithm.
Okay, thank you.
Any other questions? So can you tell a little bit about your algorithm? Just, I mean, possible?
I think that'll take a long time.
Okay, but some idea, some maybe
Okay,
possible.
so our algorithm basically works by it takes all the d-dimensional items and then it kind of flattens them to two-dimensional items. So from a d-dimensional instance, we get a two-dimensional instance. And then we try to pack that into two-dimensional bins. And then we somehow convert that two-dimensional instance back to a d-dimensional instance with only a slight increase in the number of bins. And the techniques so most of our algorithms analysis lies in this middle step where we try to pack these two-dimensional rectangles into bins. So this kind of an approach helps us get around the problem of high-dimensional packing, in the sense that two-dimensional items are much easier to visualize and reason about than d-dimensional items.
I see.
Yes, that's one of the main ideas that we use.
Got it. Okay. Okay, thank you. So I think if there are any more questions, I guess we can take it offline or maybe after the session. Thank you very much.
Thank you.
So, so we can maybe set up the second talk, yes. And it's actually time, so we can start. So I guess, yeah, we'll move on to the second talk. So Francisca will be talking about fully dynamic algorithms for Knapsack with polylog update times. So over to you, Francisca.
Thank you for the introduction. Hello from my side. I'm Francisca Eberle. I'm currently a postdoc at LSE in London, and I want to talk about dynamic knapsack because this is shorter than the actual paper title. This is joint work with Nicole Mego, Lucas Nölke, Bertrand Simon, who's also in the audience now, and Indivisible. Before I go into the details and the formal problem description, let me briefly talk about the problems we are interested in and maybe give you some idea why this is core problems, except from the fact that knapsack is one of the most fundamental problems in combinatorial optimization. So in general, in packing problems, we are always
So I'm not able to hear Francisca. So I don't know if it's a problem from, oh, now I can hear you, sorry.
Okay, sorry. Okay, can somebody maybe say if they can hear me, because.
Yeah, okay. I can hear you now, but you got cut off for like 10 seconds, yeah.
Okay, I am sorry for that. Let's hope this doesn't continue. Okay, so back to packing problems. So let's imagine you have a freight ship and you have several containers and you want to transport maybe the containers across the ocean. And of course, you should not exceed the capacity of your freight ship because otherwise your ship might just sink. And as mentioned in the previous talk, of course, when we talk about packing, then there could be other constraints that we are interested in. But for now, let's just imagine that every container comes with a weight and maybe a revenue if you successfully transport it. Another problem, not coming from logistics, but more from my daily life, would be, let's consider going on a hiking trip. And hiking usually means a lot of walking and you have to carry everything that you would like to have on your hiking trip. So this means you have to select what stuff to actually take on the hiking trip. So for example, if it's cold outside, you need to bring warm clothes. If you have to stay overnight, you also want to bring a tent. Food is also in general a good idea. And again, since we have to carry everything with us, we have to be careful in selecting because otherwise we might not even make it up to the top of the mountain. So what do these two problems have in common and how could we formalize them? I already mentioned before, in general, we say we have some items and we would like to pack these items into knapsacks. For me, items will always be the filled-in rectangles, and we are only interested in one dimension. So this means the height of the filled-in rectangle now corresponds to the size of the item. And the same for knapsacks. For me, knapsacks are again the empty rectangles now, and again, the height of such an empty rectangle corresponds to the capacity of the knapsack. And as in classical packing problems, we are now looking for a feasible solution that maybe maximizes the fun we have on our hiking trip, or that maximizes our revenue, depending on the application that we have in mind. So what does feasible here mean? Well, in general, we should not exceed the capacity of our knapsacks, and we should also not cut our item into pieces. With containers, cutting is maybe harder to achieve. For the hiking trip, it is actually not even useful to bring, let's say, half a tent up to the mountain, because, well, then it will still probably be raining into my tent during the night. But now this is the classical packing setting. So let's think for a minute, what happens if you now actually have to plan this hiking trip several weeks in advance, and you are pondering which jackets maybe to bring, because in general you have the orange one, which is the most versatile one. So you really like this one. But as the hiking trip gets closer and closer, the weather forecast maybe changes. And depending on the weather forecast, maybe the valuation for your items actually change. So now you have to be careful, and you maybe have to recompute your solution in order to still get the most out of your hiking trip. And as you ponder these decisions, which jacket should I maybe bring, or which jacket should I not bring, you talk to a lot of friends about it. And now 2 friends even decide to come with you. And now you have 3 backpacks that you could possibly use to transport stuff in the mountains. So this is what we mean when we talk about dynamic packing problems. So the instance changes. Let's formalize this. So as mentioned before, I'm talking about dynamic knapsack. So this means I'm giving n items. Every item comes with a value Vj and a size Sj. Brief reminder, sizes correspond to the height of the rectangle. On top of that, I have also m knapsacks. They might have possibly different capacities. Again, height of an empty rectangle now corresponds to the capacity of the knapsack. And the task is to find a feasible packing of a set of items such that we can maximize the value of packed items. Again, feasibly means we should not exceed capacities, and we are also not allowed to fractionally pack any items. So this is the classical multiple knapsack problem that has been investigated for several decades already. What we made out of this problem is now what actually happens if we assume that our input changes dynamically. So this could mean that from one moment to the other moment, an update happens, and maybe we now have one more item that we should consider in actually bringing. And whenever such an update happens, so an item appears or disappears, we are allowed to also update our solution and recompute the set of items that we actually bring. Now, the same could now happen also to knapsacks. We could have a knapsack appearing or maybe disappearing. And again, we are allowed to adapt our solution accordingly. Now, since these changes are only small and in some sense local, we would like to be able to efficiently recompute our solutions. Now, most of you know that already multiple knapsack, even without any dynamic changes, is strongly NP hard. So this means we don't expect to achieve to find an algorithm that always finds the optimal solution in polynomial running time. So we have 2 choices to make. Either we drop optimality conditions or we drop the polynomial running time. And since we want to efficiently recompute solutions, what we do is we drop the optimality requirement. So this means we achieve a 1 + epsilon approximate algorithm that has an update time that is only polynomial in the logarithm of n. This is the number of items, and the logarithm of m. This is the number of knapsacks. And in some sense, this is best possible because due to the strong NP hardness of the problem, we know that PTAS, so a polynomial time approximation scheme, is the best we can hope for this problem. Now, the question, of course, is how do we achieve this result? I cannot go into too much details here, but I can give you the steps that we actually do. So first of all, since we want to be logarithmic in the number of items, we cannot even read all the items in one update step. So this means we have to take our items, and whenever a new item comes, we immediately transform this item into an item type in order to get the number down to a polynomial in the logarithm of n. We call this oblivious linear grouping, and it is closely related to the classical linear grouping approach from bin packing. Once we have our item types, we now actually identify simpler subproblems and partition our knapsack accordingly. One group that we consider are what we call special knapsacks. We only have polylogarithmic many of them, but they are the largest of the instance. So we can be pretty explicit in how to actually pack them. And then we have some extra knapsacks. We will use them as resource augmentation whenever we make some errors in special or ordinary knapsacks. And whatever is left is called ordinary knapsacks, where we now have basically almost all of the knapsacks. So we have to even round the knapsacks first before we can actually start packing. Once we have identified these problems, we then actually go on and solve them. And this is exactly what the longer version on YouTube is about in my talk. And with that, I would like to thank you a lot for your attention. And now, of course, I'm happy to take any questions that you might have. Thanks.
Thank you, Franziska. Any questions?
I have a quick question, maybe.
Sure.
I guess it's a little gory, the scheme, if I recall, in terms of epsilon and stuff, the dependence. Is there a sort of a simpler scheme if all the bins are identical? I don't remember that.
Yes. So what we know is that if the bins or if the knapsacks are identical and we have many of them, then we actually get also polynomial dependency on 1 over epsilon. But of course, here the problem comes into play that if we only have 2 knapsacks, then basically even of the same size, then this already encodes, then this is basically the hard case for bin packing. So deciding whether everything fits into 2 bins or if we need 3 bins. So this means only when we have a lot of knapsacks, then we can do a better dependency on epsilon. Yeah.
Okay. Yeah. So I just forgot whether there's a dependence was better.
Yeah. So of course also, so basically if we have many identical knapsacks, we can do better. And if we only have a single knapsack, then we also have a better dependency on 1 over epsilon.
Okay. And is there a lower bound saying that you need this exponential dependence on epsilon?
I mean, yes. So in this in-between case between, let's say, 2 knapsacks and not too many knapsacks, the lower bound is this is just a hardness that basically p-tas is the best you can do, and or maybe EP-tas would be possible, but FP-tas, so polynomial dependency on epsilon on 1 over epsilon is not possible because of the strong NP hardness.
Oh yeah, that I know. I'm just wondering whether the okay, so I think I'm getting confused. When you say, I thought the dependence on epsilon was, I mean, it's just, is it n to the 1 or polynomial in 1 over epsilon?
Depending on the actual problem we are looking at, but yes, so in the most general problem, we have the n to the 1 over epsilon dependency.
Okay, I think I should look at the paper. I've forgotten the details.
And for that, so we don't have a lower bound in that sense. So a EP-tas type where we have an arbitrary function depending on 1 over epsilon times polynomial in n, this could be possible. This is something we don't know.
Okay, thank you.
Yeah.
Okay, thanks a lot. And one more question, sorry.
Yeah, I have a question. So
yeah.
in the oblivious linear grouping technique, is there a fixed function that you're using which depends on epsilon, or could it depend on the items that have been seen so far?
Okay, so what we do is we start with classifying our items according to value, and we round the values to only have 2 powers of 1 plus epsilon to have like a to already settle one of the problems. And when we now look into one of the value classes, the idea would be to as in linear grouping, to partition the items into 1 over epsilon many almost identically sized groups. And then wherever the largest group is then packed in the classical bin packing problem, we would like to shift like the second largest group and so on. So in that sense, there is a fixed function of epsilon happening here, because we always partition into 1 over epsilon, okay, more or less into 1 over epsilon many identical groups. But of course the groups then, so the group that a particular item belongs to depends heavily on which other items are in the same value class in some sense. Does this make sense? Or
so can we I mean, we're a little short on time, so yeah, maybe the next speaker can set up the slides while sorry about cutting you guys off. So maybe, yeah, until I guess Maximilian is okay, so it's ready. So okay, so we can let's start to jump to the third talk of this session. So this will be on scheduling in the secretary model, and Maximilian Janke will be giving the talk. Over to you.
Okay. Welcome to my presentation on scheduling in the secretary model. My name is Maximilian Janke, and I'm presenting joint work with Susanna Alp as my supervisor. So in this talk, we're going to study the most basic scheduling problem of make-span minimization, or one of the most basic. And here the goal is to assign jobs which are uniquely defined by their processing times to parallel and identical machines. Preemption is not allowed. And given such an assignment, the goal is to minimize the make span, which is just the time it takes to process all jobs. So it's the maximum load of the machine. And even the offline problem, it's not, it's difficult. It's at least NP complete, even though a p-test exists. So even here in the offline problem, we can improve. But this talk is going to focus on the online problem. So to an online algorithm, jobs arrive one by one, and each has to be scheduled permanently and irrevocably before the next one is revealed. So basically, we just see this one job of size 1.5, and we have to assign it. And only then do we discover that the second job arrives. And yeah, then we can go through such an online sequence. In general, it's impossible to obtain an optimum make span on such sequence, even given arbitrary computing power. Instead, one typically measures online algorithms in terms of competitive analysis. That is, one looks at the worst ratio between the online make span and the offline make span. We also talk about this adversary, which designs the worst case input sequence to compare the online and the offline algorithm to. While this adversary model is the most popular model to measure online algorithms, we are focusing on the random order model, which was designed to be less pessimistic than the adversary model. In the random order model, the job order is chosen uniformly random. So we can think of this adversary designing an input set, but before it being presented to the online algorithm, it is randomly permuted. Now, of course, the make span of the online algorithm is likely to depend on this permutation order. And thus, we consider the expected make span of the online algorithm A and compare this to the optimal make span. And the worst ratio which can occur between this expected make span and the optimal make span is then the competitive ratio in the random order model. And in our paper, in fact, we actually introduce an even stronger model. So this is a common random order model for many online problems. But for scheduling, there's actually a notion of a nearly competitive ratio, which is far less pessimistic. And here one does not only want to be C competitive in expectation, but with high probability. So an online algorithm is nearly C competitive if it is C competitive on almost all input permutation, excluding a fraction of input permutation, which vanishes for large numbers of machines. And even on these worst case instances, permutation, one needs some sort of performance guarantee. Yeah, and I mean, this is something we also studied earlier, but in this talk, I called it the secretary model. This is since we assume that the number of jobs is known in advance. And the thing is, for random order models, this is a thing which differs between problems. So sometimes n is implicitly known. For the most classic problems, such as the secretary problem, it's almost always known. And it turns out that for scheduling, it's almost always known. Besides, we actually provided the only result which does not use this knowledge a year ago. And we can show that knowing this number of jobs n in advance is fairly powerful. So let me briefly review the literature. So far it's known that the greedy algorithm, which is just a simple strategy for make-span minimization, which always uses the least loaded machine, it does not improve in the random order model, at least not for large numbers of machines. This is shown by Osborne in 2008. Then there are, as far as I'm aware, two other problems, which two other papers which analyze scheduling problems under random order arrival. And they also know the number of jobs in advance. In 2020, we already studied these problems, but we don't know the number of jobs in advance. And I mean, here we set this model apart from this deterministic adversarial model by providing 1.84 competitive algorithm, and we also had some lower bounds. Now, one problem, of course, is that it might not be fair to compare ourselves to the deterministic setting, because in the random order setting, random information is implicit. But the other problem is that randomized adversarial, the setting is poorly understood. So the lower bound is quite distant from the upper bound. And there has not been made much progress has been made. But at least if we know if we know the number of jobs in advance, we can set these models apart. So we can provide an algorithm which is 1.535 competitive, knowing the number of jobs in advance, and also some first lower bounds for this model. Now, what precisely do we do in our paper? Well, we show that knowing n is a huge advantage, at least most likely. It's not formally established yet. And I mean, the most powerful technique is certainly sampling, where we look at a small fraction of the input sequence to glimpse information about the whole sequence. Of course, sampling runs into several errors. So first of all, we don't know these estimates right from the start. And this is a big impediment if we were to just blindly adapt some prior algorithm, which, I mean, there's a setting of semi-online algorithms which know certain information right from the start. But commonly, these algorithms need to know this information right from the start and not a bit later. Then, of course, there are some margins of errors, and we also have to make our algorithms robust, that even if we have worst case sequences where our sampling estimates can be arbitrarily off, we need to perform well. And I mean, we first show in our paper that it's easy to sample the average load of the job set. And this actually allows to immediately adapt one semi-online algorithm for the setting where the average load is known. And I mean, it's not the best semi-online algorithms in this setting, but it's the only one that is adaptable. And this way you can quite easily obtain a 1.75 competitive algorithm. We then provide a more sophisticated algorithm, which is 1.535 competitive. And this uses sampling in a much broader scale. And depending on what it has learned through sampling, it has to decide between two strategies. The one is the least loaded strategy, which is an enhanced version of Graham's greedy strategy. So it's basically Graham's greedy strategy, but a few machines are kept in a reserve to capture large jobs. And a critical job strategy, which really tries to use the sampling information. And sometimes we have to switch between these strategies because our initial choice, which we made through sampling information, may be wrong. And this actually also uses some techniques which go beyond sampling. Next to this, we also provide first lower bound for the secretary model. Do they think that the upper bounds are the main result? So yeah, thank you for your attention.
Thanks a lot. Any questions? So one question I have is, what are the lower bounds that you provide? What do you mean by what's the type of lower bound that you have?
So I mean, we have this model of nearly competitiveness where we want to have the competitive ratio of high probability. And we show that this is not possible for competitive ratios below 1.257. And if you look at the classic random order model where you look at expected values, this provides a lower bound of 1.04, which is fairly low, but at least above 1. So we can show that you don't perform out very well.
I see. And these algorithm, I mean, this 1.535 that you have, there are no reassignments as the jobs arrive. Is it like it's like when a job comes, you just commit to the based on the decision of based on the sampling that you have done and the analysis.
Yes. So it's
Okay.
the online setting, so you cannot reassign jobs. But using sampling, you can look into the future, because if you see a job very often in the beginning of the sequence, and you know it's a random sequence, then it's likely to appear very often later in the sequence too, right?
Other questions? Anyone else? Okay, if not, we can thank the speaker. Thanks a lot. And we can set up the next talk, I guess. So yeah, next, I think.
Thank you.
Yeah. Yes. So Saket will be giving the next talk.
Let me set up my talk.
Yes.
Can you see my screen?
Yes, it's very clear.
Okay.
Okay,
so
we can start. So we can start.
Okay, so welcome to the talk. I'm going to give a talk on ETS-tight algorithm for multi-team formulation. And this is co-authored by Daniel, Sowasuri, Ji Zhu, and me. The talk was supposed to be given by Ji, who has given the long talk, but unfortunately he couldn't be available today. So let's immediately get into the problem. So we are going to talk about a slightly general formulation of what is known as multi-team formulation. So in this problem, there's an input which consists of candidate set C, and you have some scoring function which tells you that if you choose some particular subset of candidate, what score you get. And there are two integers alpha beta given to you, and your objective is to find alpha teams of each of size beta, and pairwise they should be disjoint, and they should be this maximizing the sum of their scores. Okay, so let's look at one example. So this scoring function has generally like some 2 power c to real numbers, and it is usually implicitly defined. And for example, if C is some set of numbers, then what is a score of C prime for some C prime subset of C? You just basically sum up the numbers. Okay. So now what we try to do, like now you generalize these numbers, like these candidates, because we are using the word candidate, from numbers to d-dimensional vectors. Okay. So now you can think of each candidate A in C as a d-dimensional vector of like in RD. And now what do they symbolize? Okay. So basically we view each dimension as a skill, and the coordinate of that dimension measures the performance of the candidate in that skill. So it is possible that one candidate could have different set of skills, and based on how much good or bad he is, we could give some score in that dimension. Okay. And so what is a team? Team is basically a subset of candidates. And what is a natural way to define the score of T is to pick the highest performance of each skill and add them up. Example, so suppose here's a team consisting of A1, A2, A3, A4, 4 people. And suppose we have 5 attributes or 5 skill sets. So each of these candidates are given the scores for each of the skills that they have. And now how do I define the score of my team? It basically for each skill, I look at which candidate has the highest. So for example, with respect to skill kappa 1, A2 has the highest, which is colored in red. So I took 4. With respect to score skill K2, A3 has the highest, so on and so forth. So that gives you the score of 24. Okay. And so we go about more general scoring. So instead of only taking the best one, we can take multiple values. For example, we have some beta, like a vector in dimension D, H1 to HD, and we take the HI highest values of the ith skill and add all the values up to get the score of this. For example, look at this. This is a team, and now suppose my H value is like 1, 2, 3, 2, 2. Then what it means that for the skill 1, I just need one person. So for this particular team, I look at the highest score which is given to a candidate, that is 4. Okay. Now, with respect to skill 2, my attribute is 2. So then I look at, okay, I need 2 top scored, which is 5 and 3, and add them up. Similarly for 3, 4, and 5. So this is how I define this more general scoring rule based on this vector H. Okay. And now notice that we are not looking for one team. We are looking for several like alpha teams we are looking for, where these teams are disjoint. Okay. And this is what is known as sum of H maxima scoring. And it was defined by Kleinberg and his co-authors in earlier papers. But now the question is, how hard is the multi-team formation with this scoring function? So earlier in 2019, Skylber, Singh, and Suri et al. Showed that multi-team formation with sum of maxima score is NP-complete, even when if you take dimension like log n, beta equal to 4, and a scoring function is like 1, 1, 1. So from each, like you are just summing the score from the each, what do you call? So you just take the top candidate with the particular skill. So now you've asked what happens if you just want one team. Then if the dimension is unbounded, you can show that this problem generalizes maximum coverage problem. So what is the maximum coverage problem? So you're given a set U and collection S of subsets of U, and you have to find K sets in S whose union contains the largest number of elements in U. So how do you model maximum coverage as multi-team formation problem? Is that your universe is nothing but set of attributes, and a candidate is a subset of this universe, which basically the set of attributes he has. Now, if you just take the union and like their union, then basically it's a set of people who has that set of skills. So this is how we can give this easy reduction, which shows that maximum coverage can be reduced in polynomial time to multi-team formation with sum of maxima scoring for alpha equal to 1. Now, what if the dimension D is small? So the earlier authors showed that this is polynomial time solvable for D at most 2. So the interesting question that was given to us was that, is this problem poly time solvable for any fixed dimension D? In fact, is this problem fixed parameter tractable with parameter D? So these are the 2 questions that we tried to answer in this paper. And what we showed that if we believe that exponential time hypothesis is right, then we cannot have any algorithm for multi-team formation with sum of maximum scoring with running time 2 power D over C for any C greater than or equal to 12. And we complement this with an FPT algorithm, which basically does multi-team formation in 2 power big O of D time. And this algorithm is achieved by basically giving a reduction to a ILP, integer linear programming, with basically f of D number of variables and what is known as n-fold ILP. It's not just ILP, but ILP with constraint matrix has some particular property, and that is the basic contribution to reformulate our problem in this what you call ILP formulation. And once we have been able to formulate our problem in this formulation, we just apply the known result about this n-fold ILP and were able to achieve this result. So that's all that I had to say. Thank you. I'm ready for any questions.
Thanks a lot, Saket. Are there any questions?
I was hoping Saket would illuminate the n-fold ILP, but I guess one should see the long talk.
Yeah, it has like long version has, because even the defining the constraint matrix is like 4 minutes work minimum.
Yeah, I know it's technical. Yeah. Anyway, I think it's a nice tool to know.
Yeah, but I think one comment I could make is like, just like maximum coverage, this also had 1 - 1 over E approximation algorithm. And like we made our own approximation algorithm, and then we found out that there's a reduction to some matroid version of coverage directly, and it gives you 1 - 1 by E approximation. Yeah. So
it's in for any D you're saying?
For any for any D, yes. I think for D constant, I'm quite sure that you can achieve 1 - 1 by E approximation.
Yeah, I mean, is it submodular maximization subject to some matroid constraint? Yeah.
Correct.
Yeah. So I guess that might be for any scoring function also, right? As long as the scoring function is submodular. Or
Correct.
Right.
Yeah, it may be worth mentioning that in the paper, I guess.
Yeah, it is. We do mention this in the paper.
Nice.
But I just forgot to put in my slide. But I thought that there are people that, at least in this session, there were approximation algorithms. Then I thought people might appreciate that.
So one other question I had is, I mean, you said sum of maxima, right? Do you know anything about the top 2 or top 3 kind of scoring functions that for this low dimensional setting?
But isn't this generalizes? Because now for each coordinate, I tell you how many can you. Like,
oh, okay. So that is what you're talking about. Sorry,
yes.
I got confused. Okay,
Yes.
okay, got it.
Yeah.
Yeah, perfect. Thanks.
So I guess the positive result applies for that general version also.
Yes,
Right.
yes,
Okay.
yes.
Yeah.
Thank you.
Can you generalize it to like more like norm-based objectives instead of like just top K norms? What if you consider like say the L2 norm of the skill set?
Oh, at least our methods won't apply. Yeah, I'm quite sure about that. Yeah, I mean, I'm not saying results may not exist. All I'm saying that at least our methods won't work. It won't reduce, at least for FPT result, it won't reduce to the kind of ILP we wanted. We did try for this, like at least L2 norm, and then we did realize that we need a completely different set of algorithmic tools. For approximation algorithm, I do not know whether it will apply or not.
Thank you.
Thank you.
Any other questions? We still have a minute more. Okay, if not, let's thank Saket again, and maybe we can have Sharath set up the slides.
Can everyone like see me properly and hear me properly and see like the transitions on the slides?
Yeah, seems to be working.
Okay, great. Thank you.
Okay, so I think it's time. So yeah, our last talk of this session will be by Sharath on approximation algorithms for flexible graph connectivity.
Thank you, Ravi. I'm Sharath Ibrahimpour. Today I'll be giving a talk on a paper titled Approximation Algorithms for Flexible Graph Connectivity. This is joint work with Joseph Cherian, Sylvia Boyd, and Arasha Dadan. So what is flexible graph connectivity? It is a non-uniform model of survivable network design introduced by Ajishwili, Hamalsheim, and Malan Taylor just last year. Okay. In an instance of FGC, we are given an undirected multigraph G on n vertices and m edges. Edges have non-negative cost. And we have a partition of the edge set into 2 parts, safe edges and unsafe edges. A property of safe edges is that they never fail. The goal in FGC is to find a minimum cost edge set F such that the subgraph V, F remains connected no matter which unsafe edge fails. That is, like, we want to protect ourselves against failure of any one unsafe edge. It's a robustness problem. In this figure, I've shown an instance of FGC. I use like solid green edges to denote safe edges, dashed red edges to denote unsafe edges, and I've mentioned the cost on the edges. One possible solution is to pick these 3 unsafe edges. Observe that no matter which unsafe edge fails, we still have connectivity in the graph. We could also have chosen like these 2 safe edges, and that's also like a feasible solution. There are many other solutions, feasible solutions for this problem. The thing to note that like all the problems that I'll be discussing in this talk today we may pick at most one copy of any edge. Okay? That's part of our model. Okay? What are some interesting special cases of FGC? If all the edges are safe, then FGC is simply the minimum cost spanning tree problem. And if all the edges are unsafe, then FGC is the minimum cost two-edge connected spanning subgraph problem. So in some sense, FGC interpolates between one-edge connectivity and two-edge connectivity. Here's the cut characterization of FGC solutions. So an edge set F is feasible for FGC if and only if on every cut S, the edge set delta S intersect F contains either a safe edge or two edges. And here, like delta S denotes the set of edges with one endpoint in S and the other endpoint outside S. Let me mention a generalization of FGC, which we introduced. It's called P, Q FGC. In this model, we have two integer parameters, P and Q. P is the connectivity parameter and Q is the robustness parameter. We have an instance of FGC again. But now what we want to do is we want to find a min cost solution that remains P edge connected against failure of any set of Q unsafe edges. Again, as you can see, like a natural cut characterization of P, Q FGC solutions is that for every cut S, we want either like F should either contain P safe edges on that cut, or it should contain some P plus Q edges. Okay? They can be like a combination of safe and unsafe edges. Two important special cases of P, Q FGC that we consider in this work are when the robustness parameter is 1, that is, we want P edge connectivity against failure of any one unsafe edge. And on the opposite end, the connectivity parameter is 1. So we want a min cost solution that remains connected against failure of any Q unsafe edges. Okay, so that's 1, Q FGC. There is another non-uniform model of survivable network design called as capacitated K-edge connected spanning subgraph problem. This was introduced by Gomans et al. Okay? And so this model has like close connections to P, Q FGC. In this model, in an instance of capacitated KECSS, we have a multigraph G and a connectivity parameter K. Every edge comes with a non-negative cost and an integer capacity UE. You can think of UE as the safety rating of the edge E. And the goal in capacitated KECSS is to find a min cost solution such that for every cut, the total capacity of F edges on that cut is at least K. In other words, we want the capacity of a global minimum cut in this subgraph to be at least K. It's just simply the capacitated version of the K-edge connected spanning subgraph problem. I'd like to again remark that if we buy an edge E, then it costs CE and gives capacity UE. We are not allowed to fractionally buy an edge. And also we can buy at most one copy of an edge. What are the connections between P, Q FGC and capacitated KECSS? If we consider P, Q FGC with P equal to 1 or Q at most 1, then it is a special case of the capacitated KECSS problem, where we set K equal to P times P plus Q. And for capacities, we assign a capacity of P plus Q for safe edges and P for unsafe edges. So if we do this, then P, Q FGC becomes like a special case of capacitated KECSS. However, general models of PQ FGC and capacitated KECSS are incomparable. In particular, PQ FGC is not equal to capacitated KECSS with this choice of K and edge capacities. Let me mention our main results in this work. What I'm going to do is I'll use like a Venn diagram. This is not exact. It's just for representative purposes. And I'll like denote the approximation ratio for each of these problems. For the most basic version of FGC, we give a 2 approximation algorithm. Next, so this result improves upon Ajeshvili et al.'s 2.527 approximation. I'd also like to remark that this 2 approximation matches the best known approximation ratio for 2 ECSS problem. So the special case of FGC when all edges are unsafe, the current best algorithm is just a 2 approximation. So we already matched that. Okay. Next, for if we want like P connectivity, pH connectivity against failure of one unsafe edge, then we give a 4 approximation. And for the other problem, the complementary problem where we want like connectivity against failure of Q unsafe edges, we give a Q plus 1 approximation. And for the most general P, Q FGC, we give ordered Q log n approximation. And for the complementary problem again, or like the orthogonal problem, capacitated KECSS, we give an approximation algorithm whose ratio is the better of these 2 functions. Like one is the connectivity parameter K, and the other one depends on the maximum edge capacity. Here, Gomez et al., like what is known in the literature is that Gomez et al. Gave a min of 2K, M approximation. Observe that our algorithm has a better dependence on K. Chakrabarty et al. Gave a randomized ordered log n approximation for this problem. So this result and this result are incomparable. This depends on the size of the graph, whereas our result does not depend on the size of the graph, but only on the edge capacities and the connectivity parameter. Okay. I'd also like to mention that for the unweighted version of FGC, we give a 1.455 approximation. This improves upon Ajeshvili et al.'s 5/3 approximation. In unweighted FGC, all the edge costs are 1. Let me quickly mention, like at a very high level, like what techniques we use. For all the problems to the right of this orange line, for these 3 problems, our approximation algorithm is based on a reduction to the minimum cost rooted K arborescence problem for a suitable choice of K. Whereas for P, 1 FGC and P, Q FGC, we give a 2-stage algorithm. In the first stage, we'll compute a solution that is mostly feasible. That is, if you look at the number of cuts that are violated, if you recall like the cut characterization of P, Q FGC solutions, then the number of cuts for which there is a violation, that number is at most a polynomial in the number of vertices. Then in the second stage, we'll like repeatedly augment the solution until all these deficient cuts are fixed. We will argue that like the number of augmentations is at most Q. I'd like to end the talk with some open problems. So in this work, we give an order Q log n approximation for PQ FGC. Can we remove the dependence on log n? It would be nice to just not have any dependence on the size of the graph. If that's like, say, even more special cases, like what can we say when Q is a constant? Say when Q is 2, is there a constant factor approximation? Even the case with P equal to 2 and Q equal to 2 is open. Next, for 1, Q FGC, we give a Q plus 1 approximation algorithm. Can we have a little OQ dependence in the approximation ratio? Or prove that this is impossible through a hardness result? Lastly, can we improve approximation ratios for P, 1 FGC and unweighted FGC? The current ratios are like 4 and 16 over 11. With this, I would like to end my talk. Thank you for your attention.
Thanks, Sharad. Are there, and to all the other speakers of the session as well, and are there any other questions for Sharad?
Any development since the paper? Any new results?
So in the paper, for P, Q Fgc, we got like a deterministic order Q log n approximation. In the introduction, we had mentioned only for like when Q is order P, but we are able to like remove that dependence assumption on like P and Q. So any values of P and Q, we give a deterministic order Q log n approximation.
Okay.
And this we are like submitting to a journal, so it will probably like take some time to appear.
Yeah, thank you.
Thanks for your comments, by the way, during like,
and the deterministic is based on what?
So what we do is like we actually use capacitated KECSS for P, Q Fgc to obtain like a starting solution, and then so basically like we in this two-stage algorithm, we start with a capacitated KECSS instance with these natural like capacities, and then this solution we argue that like if any deficient cut is like a near minimum cut, and in this like capacitated subgraph, so we can enumerate all of them using like Nagamochi et al.'s result. Deterministically, we can obtain all near min cuts, and then we just use hitting set algorithm to augment these. Yeah, so it's a very simple algorithm.
So thank you.
You're welcome.
So the last slide you mentioned one of the open questions is you said even 2,2
FGC is
flexible. Yes. FGC is open. That means what? So every cut should either have 2 safe edges or 4 edges in total.
4 edges in total.
And the best known algorithm for this is the log n that you mentioned from the bullet point.
Exactly. So it's order log n. Yes.
Okay. And are there any lower bounds known for any of these questions beyond constants?
Unfortunately not. Yes. Okay. We are also thinking about that, and it would be nice if we could like show some omega Q hardness, or just like beat this, obtain like a little bit Q. Yeah. It seems like robustness does cause like a lot of loss in approximation. At the moment, like we are more interested in getting rid of like the log independence. Like trying to like exploit like the cut structure or something, like just the structure of near min cuts or something like that.
Okay.
We haven't made any headway.
Okay. If there are no other questions, let's thank Sharad and also all the other speakers of the session. So thanks everyone, and I guess there's a break now. It's 25 minutes break, and next session starts at in 22 minutes from now. Thank you.
Thank you for hosting the session.
So let's begin with some definitions. So graph is said to be C-closed if for every pair of non-adjacent vertices, they share at most C common neighbors, right? So for example, a clique is 1 closed and a star graph is 2 closed, right? And a slightly weaker notion, a graph is said to be weakly gamma closed if for every induced subgraph, there exists a vertex which shares at most gamma common neighbors with all of its non-adjacent vertices. Yeah. So the closure of a graph G is the smallest C such that G is C closed, and the weak closure of a graph G is the smallest gamma such that G is weakly gamma closed. So closure and weak closure of a graph are properties which have been introduced very recently. So one second. So let's see why they're interesting. The closure of a graph is no more than max degree plus 1 and the weak closure of a graph is never more than degeneracy plus 1, right? So why is the closure of a graph never more than max degree plus 1? It's very easy to see, right? So if two vertices can never have more than max degree common neighbors, right? And so you get the bound very easily. And for weak closure, similar to degeneracy ordering, for weakly closed graphs also, we can define a weak closure ordering, and using that we can show that the weak closure is never more than the degeneracy. Okay, so and as you all know, max degree and degeneracy are like interesting parameters which have been well studied in literature, right? And since closure and weak closure are never more than these two, it's really interesting to study these parameters. And also these parameters can be computed in polynomial time. Another motivation for these parameters is that they capture sparseness and triadic closure in real world graphs. So what is the triadic closure property? So if you take a social network of friends, right? If two people share many common friends, then it's very highly likely that these two are friends themselves, right? So that's the triadic closure property, and these parameters capture this property, right? So this table summarizes C closure and V closure of some well-studied social networks. So if you see this table, if you look at the second graph, right? The graph has nearly 40,000 edges, but the weak closure is just 8. So even from the real world perspective, these parameters, the weak closure is found to be small for real world social networks, and thus it's motivating to study weak closure and closure as a parameter from FPT perspective. Okay. So let's look at a little bit background about this problem. So these two parameters were introduced by Jacob, Tim, Sheshadri, Fan, and Nicole. And there's been a number of works using these parameters. Tomohiro, Christian, and Frank began the systematic study of parameterized complexity of computational problems using weak closure and closure as parameters. And there's disjoint work by Edin and Tim also for FPT algorithms for some problems on C-closed graphs. Right. So the work that we have is based on an open problem by Tomohiro, Christian, and Frank. Let's go dive into the problem. So the problem at hand is dominating set in weakly gamma closed graphs. So what is a dominating set? I'll recall that a dominating set of a graph is a set such that either for every vertex in the graph, either it's contained in the dominating set or has a vertex adjacent to it in the dominating set, right? So the problem at hand is that you're given a weakly gamma closed graph and k, a non-negative integer k as input. And our question is, okay, can we find a dominating set of size at most k for this graph? And so the open question that Tomohiro, Christian, and Frank asked was, okay, is this problem FPT when parameterized by gamma and k? They showed in their ISIC paper that the problem is FPT when parameterized by closure, right? C and k. And they asked the question for weakly gamma closed graph. And in this paper, we answered this question positively with a yes. Okay, so let's move on to our result. So our main result is resolving their open problem by saying that, yes, dominating set in weakly gamma closed graph is FPT. And the runtime of our algorithm is k to the gamma squared k cubed poly n. Along the way, we also obtain other results. So we show that every weakly gamma closed graph has VC dimension at most 6 gamma. So for those of you who know what is VC dimension of set systems, the VC dimension of a graph is nothing but the VC dimension of the set system where the universe is the set of all vertices of the graph, and the family contains the close neighborhood for every vertex in the graph, right? And this bound is essentially tight in the sense that we can construct weakly gamma closed graph which has VC dimension gamma. So up until the constant of 6, the bound is tight. Okay, so why is this result even useful? So the VC dimension bound helped us improve our runtime from double exponential to single exponential. And apart from that, it also helped us to obtain an approximation for this problem. So we were able to obtain an order gamma log gamma k approximation for this problem, right? So this approximation is just using the bound on VC dimension and applying known results for set cover on set systems of bounded VC dimension. Okay, and looking at this approximation ratio, a natural question is to ask whether for fixed gamma, there is a constant factor approximation for this problem on weakly gamma closed graph, right? So why is it natural? Because for degenerate graphs, degenerate graphs, it's known that there is a constant factor approximation when D is fixed, right? But it turns out for fixed gamma, there's no constant factor approximation, and it's a small reduction, which you can see in the paper. Okay. With that, let me quickly dive into the techniques that we use for our main result. So we use something called as domination cores as a main part of our result, right? So a domination core is nothing but a set of vertices such that every set of size at most k that dominates this set dominates the whole graph. So if we have a domination core, then it's enough for us to just find a dominating set that dominates this domination core, right? A trivial domination core is the set of all vertices of a graph. But why are they useful? So small domination cores directly imply an FPT algorithm for dominating set. Let's see why that is so. It's a very simple algorithm. So suppose you have a domination core of size f of gamma comma k, right? Then my goal is to find a dominating set of this domination core, right? So now I'm going to guess the neighborhood of the vertex in the dominating set that we are trying to find into D. Right? So you guess the neighborhood for each of the k vertices that we are trying to find, guess the neighborhood into D, right? And then check whether such a vertex exists in G, right? And if over all guesses it's you are not able to find such vertices, then you return no. Otherwise, you obtain a dominating set. The runtime of this algorithm is 2 to the f of gamma comma k poly n. Why is that so? Because the number of neighborhood choices into D is 2 to the size of D, which is 2 to the f of gamma comma k. But using our VC dimension result, we can reduce the number of neighborhoods into D to f of gamma comma k to the 6 gamma. And essentially, this helps us bound the running time from double exponential to single exponential, right? So the goal finally using this reduces to finding a small domination core, right? And for finding a small domination core, what we essentially do is we bound the size of minimal domination cores. So what are minimal domination core? A minimal domination core is the domination core in which you cannot delete any vertex. So deleting any vertex in the domination core results in a set which is no more a domination core, right? So if we can bound the size, then the simple algorithm is start with a trivial domination core, which is set of all vertices, remove a vertex from it. There exists such a vertex because the domination core is of large size. And you keep removing vertex until you get the bound. And finally, you have a domination core of small size, and you find a dominating set for it using the previous algorithm that we saw, right? So the main step here is proving that large minimal domination cores, there are no large minimal domination cores in weakly gamma closed graph. So we bound the size of minimal domination cores. And for this, what we do is we keep digging structure in our graph. We keep finding highly structured induced subgraphs, which finally yields us one of these 3 pattern graphs, which we can show to be not weakly gamma closed. Or therefore, what happened? We started with a weakly gamma closed graph, but we showed that if there is a large minimal domination core, there's a large weakly closed induced subgraph. This cannot be true because weak closure is closed undertaking subgraphs, and thus the graph cannot have large minimal domination cores. And for this purpose, we use Ramsey theory. So let me conclude. So in conclusion, we gave an FPT algorithm for dominating set in weakly gamma closed graph that runs in k to the gamma squared k cube poly n time. And this resolves the open question that whether this problem is FPT in weakly gamma closed graphs. And we also gave a bound on VC dimension of weakly gamma closed graph, which we believe will find uses in further study of weakly gamma closed graph. A nice open problem in this area is whether, in respect to this problem, is whether dominating set in weakly gamma closed graph admits a polykernel. That is there a kernel of size k to the f of gamma for some function f? Thank you.
Thank you, Vaishali, for the wonderful talk. Are there any questions from the audience? Okay, so while we wait for audience question, okay, so
I have a question.
I have a question, yeah.
Sure.
So, I mean, you showed a table with the weak closure parameter. I would have liked to see a table with dominating set size.
Okay.
So, I mean, if you give me an FPT algorithm, should we expect these graphs to have small dominating sets or big dominating sets, right? It's not clear a priori, right? The closure might be small, but some of these parameters could be large, no? It could be, the FET is interesting if you believe that the parameter of interest here, the dominating set, is small. If it is big, then FPT doesn't really help, right?
Yeah, that's true. But if you see degenerate graphs, right? Degenerate graphs. So like dominating set for degenerate graph has been studied with parameter D and K, right? And weak closure is never more than the degeneracy. So because FPT algorithms have been studied with D and K as parameter, it's interesting to study with.
I don't know. I'm a theoretician too. I'm just saying that it's nice to kind of get a sense of sometimes this real world graphs, right? Because the whole notion of closure itself is based on somehow that it is interesting because of this triadic closure property.
Yeah,
right?
that's true.
So it would be nice to know. I mean, independent of the theoretical work, it would be nice to know some estimates. Should we expect these graphs to have what should we expect? We can solve the LP and see a lower bound on the dominating set size just for fun. That's
sure.
all.
Yeah.
Okay.
Yeah. It'll be nice to look at that. Yeah, I'll look into it. Thanks.
Oh, sorry, I forgot to unmute. Thank you, Vaishali. In interest of time, we'll move to next speaker. Next speaker is Kavita.
Yeah, thank you.
Thank you. Okay, so yeah. Kavita will be speaking on matchings, critical nodes, and popular solutions.
Thanks. Am I audible?
Yes, you're audible.
Yeah, thanks. Thanks, Kirti. So our input is a bipartite graph where every node has a strict ranking of its neighbors, as shown in this example here. What one typically seeks here is a stable matching. A matching is stable if there is no edge that blocks it. This blue matching is stable here. Gale and Shapley showed that stable matchings always exist in bipartite graphs, and their algorithm finds one in linear time. There may be many stable matchings in the given graph. Interestingly, all of them match the same subset of nodes. Suppose some nodes are marked critical, and we're interested in only those matchings that match as many critical nodes as possible. Say these 4 nodes are marked critical, and the stable matching leaves 2 of them unmatched, while this red matching matches all of them. Only such matchings will be considered admissible solutions for us, and let's call such a matching critical. Critical matchings are relevant in many applications, such as allocation problems in humanitarian organizations and so on. So our goal is to find a critical matching that is optimal as per node preferences. What is optimal? We'll define it now. We say matching M is at least as good as matching M prime if the number of nodes that prefer M is at least the number that prefer M prime. A node prefers the matching where it gets a better partner. A popular matching is one that has no better matching, so it is at least as good as any matching. Popular matchings always exist because stable matchings are popular. So let's ask for a critical matching such that there is no better critical matching. So our critical matching M is at least as good as any critical matching, and we'll call this matching M a popular critical matching. Does such a matching always exist? Is it easy to find one? Is it easy to find a max size such matching? We consider these problems here and show positive answers to all of them. The max size popular matching problem was considered a few years ago, So this is a maximum matching such that there is no better maximum matching. It was shown in this paper that such a maximum matching always exists and can be efficiently found. Our algorithm is based on this algorithm, which is a multi-level Gale-Shapley algorithm. Recall the Gale-Shapley algorithm. It's very simple. Nodes in A propose and nodes in B dispose. So in this algorithm, every node in A has a level assigned to it. To begin with, all nodes are in level 0. Let's run Gale-Shapley algorithm. Nodes in A that get rejected by all neighbors promote themselves one level higher. Nodes in B will prefer higher level neighbors to lower level neighbors. So these rejected nodes, which are now at a higher level, may find partners, and so the Gale-Shapley algorithm continues. We borrow this idea. Nodes in B prefer higher level neighbors to lower level neighbors. And now we say nodes in A prefer lower level neighbors to higher level ones. So there is a basic level, level 0, and alpha positive levels and beta negative levels. And only critical nodes of A will be allowed in the positive levels, and only critical nodes of B will be allowed in the negative levels. The intuition behind our algorithm is as shown in this figure. To begin with, let all nodes be in level 0. Let's run Gale-Shapley algorithm. Unmatched non-critical nodes will remain in level 0, while unmatched critical nodes of A can promote themselves to higher levels and begin proposing again, while unmatched critical nodes of B demote themselves. But you see, nodes in A prefer lower level neighbors to higher level ones. So these demoted nodes should actually have received a proposal even earlier. So formally, in our algorithm, all nodes of A start at the lowest possible level, that's level minus beta. Let's run Gale-Shapley algorithm. And in negative levels, proposals can be made only to critical nodes of B. So only critical neighbors of these nodes will receive proposals. And while there exists nodes in A that are not yet matched by any neighbor, they are allowed to promote themselves to higher levels. And while in negative level, a node can propose only to its critical neighbors. In level 0, they're free to propose to any neighbor. So that's the first while loop. At the end of the first while loop, if there are still unmatched nodes in A, the unmatched critical nodes can promote themselves even higher. They can move to positive levels. And now they can propose to all their neighbors, critical and non-critical. So the Gale-Shapley algorithm continues. So at the end of the algorithm, we have a partition of the node set as shown here. So this partition is determined by the level of the nodes at the end of the algorithm. There is a lot of structure here, and this structure allows us to show that the matching computed by this algorithm is critical. To show it is popular among critical matchings, we'll use the LP method. This is the dual LP of the max weight critical matching LP. So the matching M computed by our algorithm is implicitly present here via edge weights. The weight of an edge is a function of the matching M. So the variables here are YU, ZA, ZB, and KA, KB are defined below. They are the number of critical nodes of A and B matched in the matching M. And the weight, as I said, of an edge depends on what the endpoints of the edge got matched to in the matching M. And it follows from LP duality that if the optimal value of this LP is at post 0, then M is a popular critical matching. And we construct such a feasible solution. In fact, this will be an optimal solution, and complementary slackness will imply that the matching M is a min-size popular critical matching. In order to find a max-size popular critical matching, the algorithm is very similar. The one difference is we have one extra positive level now. Earlier, the highest level was alpha, and now it's alpha plus 1. The rest of the algorithm is exactly the same as in the min-size popular critical matching algorithm. So it is both in level 0 and level 1 that non-critical nodes are, all the nodes are present. Earlier, it was only in level 0 that all nodes were present, and now it's in 2 levels, all nodes are present. And in fact, what is happening in these 2 levels is a 2-level Gale-Shapley algorithm, which is the same as the max-size popular matching algorithm. And only critical nodes of A will be allowed to go even higher, that is levels 2, 3, so on. And as before, critical nodes of B can be demoted downwards. That's the intuition. Of course, the formal algorithm is as shown earlier. That is, it's analogous to that algorithm. And similarly, we can show the matching computed is critical. And we use the LP method to show is in fact popular among critical matchings. And this time, complementary slackness will let us show that this matching is a max size popular critical matching. So a closely related problem has been studied in another paper in this FSTTCS. In fact, that's the next presentation. Thank you.
And thank you, Kavita. Are there any questions from the audience? I had a question. In the paper, you had mentioned that the time complexity is number of edges into the number of critical nodes. So how
Yes.
hard will it be to improve the bound?
Yeah, so that's a very nice question, because even for the popular maximum matching algorithm, the running time we have is order n times m, where n is a number
Yes.
of nodes and m is a number of edges. So we don't know how to improve it to square root n times m. So I guess that would be the first improvement. And once we get that, then we could look to generalize it to this case as well. But you're right. So the number of critical, so the running time, as Kirti said, is the size of the critical set times number of edges. So when the critical size is theta of n, this is, yeah, so it takes about order nm time. Can we do it faster? Indeed, I don't know.
Okay. Thank you. Any other questions from the audience? I had one another question.
Sure.
You had mentioned that for this problem of computing best critical matching, that's NP hard. So are there any approximations of the sort that if you want to match, say, only some constant fraction of maximum matchable critical nodes?
So you're talking about the stable matching, right? The one with the least number of blocking edges. Yeah. So, so the problem that Kirti is mentioning is, if you want to find a natural relaxation of stability, is to ask for a matching with the least number of blocking edges. So this problem was considered more than 10 years ago, where they showed that finding a maximum matching with the least number of blocking edges is NP hard, and it's hard to approximate to any Poillian factor actually. So approximating it to n to the 1 minus epsilon for any epsilon is NP hard. So it's hard to approximate as well.
Okay, okay, I see.
So in the maximum matching case, all nodes are critical. So,
okay.
So that shows even for critical matchings, it would be hard.
Okay. Okay, so thank you so much, Kavita.
Thank you.
Our next talk is by Keshav Ranjan, and the title of the talk is Popular Matchings in the Hospital Residence Problem with Two-Sided Lower Quotas.
Yeah, hello everyone, thanks. So my name is Keshav Ranjan, and title of the work is Popular Matchings in the Hospital Residence Problem with Two-Sided Lower Quotas. This is a joint work with Professor Meghna Asre, Professor Prajakta Nimborkar, and Ankita Sarkar. So the problem setup for HR2LQ, that is hospital resident problem, when agents on both of the sides are allowed to have lower quotas, consists of two sets of agents, residents and hospitals. Each agent strictly rank all of its neighbors and specify lower quota and an upper quota. Upper quota of each resident is 1, and hence the lower quota of a resident can either be 0 or 1. Our goal is to compute a matching which respects the lower quota and upper quota of every agent. We call such a matching as feasible matching. Matching should also be optimal in the sense that it should respect the preference list of each of the agent. One of the classical example of optimal matching is stable matching, which is characterized by the absence of blocking agent. But an HR to LQ instance may not admit a matching which is feasible as well as stable. The 2x2 instance shown on the screen here is such an example. So we study another notion of optimality called popularity, which was introduced by Garden Force in 1975. It provides overall stability because majority of agents do not wish to deviate from it. Here we can compare any two matching in head-to-head election where agent cast votes. So an agent will cast its vote for matching in which it gets better partner, and an agent can cast up to upper quota many votes, but for those positions which are filled, which is indifferent between both the matchings, it refrains from voting. So although H1 has quota 2, it casts only one vote, and that vote goes into the favor of purple matching M here. So we see that here purple matching M gets more votes than blue matching N, and hence it is more popular than the blue matching. So we define a matching M as a popular matching if no other matching is more popular than it. Now our goal in HR to LQ instance is to compute a matching which is popular amongst the set of feasible matching. In this work, we have shown that if an HR to LQ instance admits a feasible matching, then popular matching amongst the set of feasible matching always exists, and it can be efficiently computed. These are the related works in this line, and the latest one is by Kavita in the same conference, and we have listened to her talk just a few minutes back. So let us look at the algorithm overview. Here we are given an HR to LQ instance G, and we use a reduction procedure. So assuming that an agent with positive lower quota is called lower quota agent or LQ agent, we create sufficiently large number of level copies of each of the lower quota agent. We call this agent level copies as level 0 copy, level 1 copy, and so on. To ensure the feasibility, we also create sufficiently large number of dummy agents corresponding to each lower quota agent. And for non-lower quota agent, we create only one copy. So because of these multiple level copies, the preference list of each of the agents are blown up. And here, no any agent is having lower quota. So every agent only specify upper quota, and hence we get an HR instance G prime. Now we run well-known standard Gale and Shapley algorithm on G prime to get a stable matching MS. So the edges in G prime is such that at most one of its endpoint can be a dummy vertex. And we have shown that if none of the endpoint of an edge in a stable matching is a dummy vertex, then one of its endpoint must be a level 0 copy. And based on this, we define a mapping function which maps the edges of the form RIH0 or R0HJ to an edge RH, which corresponds to an edge in original instance. And in this way, we get a matching M. Now it requires a proof that this matching M is feasible for the original instance G. And for that, we use the theory of alternating paths and alternating cycle. So by assuming that matching M is feasible, we are going to see the technique for proving the popularity, which is inspired by the work of Brandon and Kavita, where they prove the popularity for many-to-many setting without lower quota. So here we are given HR to LQ instance G and a feasible matching M. We construct a weighted bipartite graph GM, and there an agent complete one-to-one matching M star. So we convert many-to-one matching M to an one-to-one matching M star. The weight of an edge here is sum of the votes of the endpoint when endpoint casts their vote compared to matching M star. So every edge in M star will have weight equal to 0, and hence weight of M star is 0. So to prove the popularity of matching M, we just need to show that every agent complete matching has weight at most 0. And for that, we use linear programming framework. We write linear program for maximum weight agent complete matching, and then we exhibit a dual feasible solution with value 0. So recall, we constructed HR instance G prime, and there we computed a stable matching MS, and from which get mapped to matching M. And for proving popularity, that many to one matching M got converted to M star. So that 1-to-1 matching M star, we view the edges of that matching M star using the labels assigned to the endpoint of those edges in a stable matching MS, which means we look all the edges in a particular way, which allow us to assign dual values. So recall, if none of the endpoint of an edge in MS is a dummy vertex, then one of the endpoint must be a level 0 copy. And based on this, we partition the whole vertex set into 4 major parts. Level 0 hospital, higher level hospital, level 0 resident, and higher level residents. And based on the exact value of I and j, here we further define this partition. So let us take a look at using an example. So consider Rx hy is an edge in the original instance, and Rx level 0 copy is matched to hy level 2 copy in stable matching MS. So since hy higher level copy is matched, we put hy into h1, that is higher level hospital partition, and its exact level is 2, so we put hy into h12, and its matched resident goes into r02. Similarly, we do this for all the edges. Now, if we assign the edge direction from left to right to all the edges, then we see that all the edges which are blocking to MS, those edges will go upward. Means all the +2 weight edge, means edge having weight 2 will go upward, and an edge which go 1 level downward. So the endpoint of such an edge are happy with the current assignment, means MS. So they do not prefer each other, and they will get so such an edge will get -2 volt. And an edge which go at least 2 level downward are not possible. So no steep downward edges are there. So based on these 3 properties, we assign +2k -2k to each of the endpoint of every edge, where k is linear. So and since this M star is an agent complete matching, the total dual sum is 0. And using this, we prove the popularity of M. So the natural follow-up of this work is to extend this work to many setting when both sides are allowed to have lower quotas. We call such a setting as a student course allocation problem with two-sided lower quota, or in short, SC12. Thank you. Thank you very much.
Thank you, Keshav. Nice talk. Are there any questions from audience?
I think the two results are very similar, right? They're equivalent. I didn't know whether the techniques or the ideas are similar, or can the authors clarify? I'm not an expert in this.
Yeah, so the techniques are similar, but it looks like the work by Kavita, that work that is means her work is like, so we are our algorithm is reduction based algorithm, and we are looking for proposal based algorithm. So we did not, till now we are not able to find proposal based algorithm, but Kavita's algorithm looks like it is proposal based algorithm, and from that, but her paper consists the reduction algorithm, but in presentation, as she talks about, it looks like proposal based. So I'm not very sure about that, whether it is proposal based or not, but yeah, I think that techniques are almost similar.
Yeah, so I think in a way they are quite similar, but they want certain nodes to always be matched, whereas I have a certain set of nodes and I want the maximum number to be matched. So I have no nodes that are forced to be matched. So there are some subtle differences perhaps. And
is the problem the same? I thought
the problem is not exactly the same, because they have certain nodes that have to be matched, whereas I have a set of nodes, I want as many of them as possible to be matched. So there is There's nothing like this
Yes, so
particular node has to be matched.
I see.
So the critical matching, definition of critical matching considered by her is more general than the definition of feasible matching considered by our work.
And they have capacities.
And our
I have
work
no
is
capacity, so there are some differences for
The
sure.
capacities are, that's not critical. Let's not critical in my view, right? Because you can split the nodes, I think, right? Because feasibility. So also, I mean, in your work, since you want to do a max, but the number is known. I mean, that's not that's invariant, right? You know that.
Absolutely, because we could anyway compute a matching that matches as many of those nodes in that set as possible. So indeed.
So yeah, it's okay. Yeah, all right. I guess so that there is some difference that you don't force all of them to be matched. You want the max among the critical nodes.
Exactly, and I'm also not sure. So the popularity within the critical set I show by building these dual certificates. So I'm not sure if they build dual certificates. I didn't catch that part so clearly, but all of them in a way are follow-ups of that popular maximum matching algorithm, where you run multi-level Gale-Shapley algorithm, and now you selectively promote. So that promoted all unmatched nodes now selectively promote at a high level. All of them basically are sort of building on the spirit of that previous 2014 paper, I would say.
Yeah. So one question is sorry, I don't know if there's time, Kirti, for the question. One more question, or is it?
Yeah, sure.
So is there a polyhedral view of this? You know, can you sort of, instead of, is there a way to say, is it because some max weight versions are hard?
Yeah, so the popular matching polytope has near exponential extension complexity. So even when there are no critical nodes, when the critical set is empty, to describe the polytope is hard.
I see.
So, unconditionally hard, actually.
So only the fact that it's unweighted is helping here.
Indeed, there are no costs. Indeed.
Yeah.
So we just want to find the existence. So finding one popular matching is easy. In fact, any stable matching is easy. And here also we're just talking about the existence of such a matching rather than finding whatever a min cost such one or so on. Those
are hard. Okay.
Sure. Thanks.
Thanks for clarification.
Thanks, Kavita and Keshav. We now move to the final talk of this session. It's by Aniket, and he'll tell us about fair and efficient allocations of indivisible public goods. Over to you, Aniket.
Hi, okay, thanks, Kirti. Am I audible?
Yes.
Okay. So let me get started. My name is Aniket Murekar. I'm a PhD student at the University of Illinois at Urbana-Champaign. So today I'll be talking about fair and efficient allocations of indivisible public goods. This is joint work with my advisor Jugal Garg and Pooja Kulkarni, who is a PhD student here.
Aniket,
can you work on the problem of discrete fair division, which dates back to the work of Steinhaus in 1948. So he introduced the
Aniket, so we are not able to see next slide. Can you make it
a full screen?
Full screen.
So that, I think you're not in.
Is this visible now?
It is, but yeah, okay, better, yeah.
Okay.
I see. I don't know what's happening. Okay, we are seeing the outline, and okay, that keep going.
Okay, sorry about that. Right. So I was saying that Steinhaus introduced the problem of cake cutting, where we want to divide a resource such as a cake to agents who have different preferences over which parts of the cake they'd like to receive. And we want this resulting allocation to be such that the agents perceive the allocation as fair. Now, unlike cake division, where the resource is divisible, we consider the discrete setting where goods or resources are indivisible and cannot be divided and shared fractionally. So what kind of resources do we consider? Resources can be either private or public. So private goods give utility only to the agent it is assigned to, like a piece of jewelry. In contrast, public goods give utility to multiple agents simultaneously, like a book in a public library or a park or a road. Now the private goods model has
Slides are
been
not moving.
slides are not. Oh, sorry
No.
about that. Maybe let me just present it this way. I think this is visible.
Yeah.
Okay. Okay, so let me talk about the private goods model. This is well studied in literature, and so here we have a set of n agents as shown on the left, and a set of m private goods as shown on the right. Now these agents express their preferences over these goods using these valuation functions v1 through vn. And typically we assume additivity, which means that the value that an agent has for a set of items is the sum of values that she has for individual items in that set. So an allocation here simply consists of a partition of these m items into n sets. Now, let me introduce the public goods model. Here, once again, we have a set of n agents, and we have a set of m public goods. We also have a parameter k, which specifies the cardinality of feasible allocation. So an allocation in this model is simply a subset of the public goods of cardinality at most k. Here, k is 3. One can think of k as a collective budget that the agents have, which they want to spend on buying public goods, each of which are priced at 1. So this interpretation shows how the public goods model is related to problems of participatory budgeting. One can also see how it's related to voting, where n agents have to select k candidates out of a pool of m candidates. So traditionally, the case of k less than n is well studied because it captures scenarios like voting and committee selection. Once again, just to remind you, k here is the parameter k is the cardinality of feasible allocations, and n is the number of agents. So in contrast to the k less than n case, which is relatively well studied, the case of k being at least n is not well studied. However, it does capture practical scenarios. For example, a public library who is trying to buy books which cater to the preferences of its n readers will typically find that k is at least n. And there are other important examples as well. Our problem, therefore, is the fair allocation of public goods where k is at least n. So what do I mean by fair here? The central notion of fairness is proportionality. So here we say an allocation x is proportional if every agent I gets a value under x, which is at least her proportional share. So the proportional share of an agent is 1/n of the value that agent I has for her best possible allocation. So for example, if there are 2 agents here, every agent should get at least half the value of her best possible allocation. Now in additivity, using under additivity, the best possible allocation for an agent is simply the set containing the best k items for that agent. So it turns out that it's not always possible to guarantee proportional allocations in the discrete setting. So what we settle for is a relaxation called proportionality up to 1 good, which essentially says that an allocation x is prop 1 if for every agent I, there is a way to swap a good g, which is in the allocation, with a good g prime, which is possibly not in the allocation. And after doing this swap, the agent gets a value which exceeds her proportion. If this happens for every agent I, we say that this allocation is prop 1 or approximately proportional. Upfront, it's not clear if prop 1 allocations even exist. So a natural question to ask is, can we obtain prop 1 allocations in public goods? And can we obtain them in conjunction with the efficiency notion of Pareto optimization? Now, such results are known for the private goods setting. And a central concept in ensuring, in guaranteeing fair and efficient allocation is the concept of maximum Nash welfare. So the allocation, so the Nash welfare of an allocation is simply the geometric mean of agents' valuations under X. So all you do is, given an allocation X, you find out the values that agent gets under X, you multiply them, and you raise them to the power of 1 over n. So it's known that the allocation which maximizes Nash welfare is fair and efficient for private goods. And these fairness notions include NV freeness and also the relaxation of proportionality I mentioned on the previous slide, as appropriately applied to private goods. So a natural question to ask is if the Nash welfare allocation is similarly fair and efficient for public goods. So our first result shows that that is indeed the case. For public goods, the allocation that maximizes Nash welfare is fair, it's proportional up to one good, it's economically efficient in the sense that it's Pareto optimal, and it's also fair in the sense that it satisfies an approximation of the fairness notion of the round robin share. However, computationally, the maximum Nash welfare problem is NP hard, and we show that this hardness holds even when there are only two agents, or if agents only have binary values. Now, in contrast, in the private good settings, when agents have binary valuations, we have a polynomial time algorithm for computing the maximum Nash welfare allocation. So given this computational hardness, we turn to approximation algorithms and special algorithms for special cases. We show that there is an O of n factor approximation algorithm, and this applies when agent valuations are subadditive. Additionally, we also give a pseudo polynomial time algorithm when the number of agents is constant. So before I talk about my last result, I'll introduce this model of public decision making, which was introduced by Konitzer, Freeman, and Cha in 2017. Here, once again, we have a set of n agents, and instead of public goods, we have a set of m public issues. So, and each issue has a set of alternatives. So for example, in this example, we have two issues. These two agents are trying to decide what to eat and what to watch. Now, an allocation here simply comprises of a decision on each issue. And the valuation functions are set up which specify how much each agent values each alternative of each issue. Now, we've seen these three different models of collective decision making or allocating public goods. One is the model of private goods, the other is the model of public goods, and the one I just introduced is the model of public decision making. Up front, there don't seem to be any connections between these models. They seem to be unrelated. But surprisingly, we show that there are polynomial time reductions between the Nash welfare problem in these models. So specifically, we show that the private goods, the problem of Nash welfare in private goods reduces to the problem of Nash welfare in public goods, which reduces to the problem of Nash welfare in public decision making. These reductions also allow us to infer implications on the computational complexity of the problem of maximizing Nash welfare in public decision making, apart from providing crucial insights between relating these models. This is the technically most involved result of our work, and I encourage you to check out the full version of my talk or read our paper. That brings me to the end of my talk. I'll be happy to answer questions if there are any.
Thanks, Aniket. It was a very nice talk. Any questions from audience?
I have a question. So,
yeah,
are there real life scenarios where the instances are large enough that we need to worry about the complexity of our algorithms, as in the brute force algorithms will stop?
Yeah, certainly. In at least in the public goods model, certainly you would have to worry about these. For example, the participatory budgeting problem is well studied. So people elicit values from agents. So for example, you have the budget of a city, and they're trying to decide how this budget should be spread across different projects. And what you do is you ask every agent to essentially solve a knapsack problem and somehow come up with a clever way of combining these solutions from different agents to ensure that the resulting allocation is fair. And this is being implemented in Toronto and other cities as well. when goods are private as well, typically we see settings which are discrete, which are small. You have like 5 agents trying to divide at most 10 items and so on, where mostly it's okay to run your brute force algorithms. However, some fairness notions which I didn't describe here, it's not even known if they exist, even when the number of agents is quite small. So there are some very interesting questions there too. Yeah.
Okay. Also for the public good settings, so here we took an integer k, and we say that we'll only select k goods, but instead of that, if we have a weight associated with each good and we need to pick so something like a knapsack kind of a problem.
Right, right.
Does
yeah,
it,
that would be the next natural generalization. So obviously the hardness results would certainly go through, but we would have to define the notion of proportionality carefully. And we haven't been able to show that the Nash welfare allocation is still proportional. So you would have to say that there is a way of swapping items which does not exceed the budget constraint and still gives a proportional. So that's not clear. Another open question is, can we show an approximation algorithm when valuations are binary in the public good setting? Now, subsequent to our paper at FSTTCS, we were able to show that this problem is APX hard when agents are binary valuation. So we do have a lower bound, but an upper bound is still open.
Okay.
So could you give some idea behind your pseudo polynomial time algorithm?
Oh, it's a very simple dynamic programming based algorithm. Yeah, because number of agents is constant, you can essentially do an enumeration.
Because for private goods, the EF1 plus PO pseudo polynomial time algorithm is more complicated, right?
Yeah, that's true. Yeah.
But you have constant.
Yeah, here you have constantly many agents. So the natural market for public goods is something called the Lindahl equilibrium, which is easy to compute. You can write a convex program that computes it. But showing that you can round it easily and that gives meaningful guarantees, not clear.
Thanks.
Any other questions? Okay, so if there are no questions, thanks Aniket. Thanks to all the speakers of this session.
And reminder about the last bit of there is a invited talk in a little bit. Yeah, hope many of you attend that.